y equal to 3x into x plus 7 by x plus 5 plus 4. This represents the total cost for x units of output. For x units of output, the total cost. Now, according to question, we have to show that marginal cost falls continuously. Marginal cost falls continuously as the output is increasing. Now, how to get marginal cost? Marginal cost is the rate of change of total cost with respect to the output unit. That is marginal cost is given by dx of marginal cost rate is given by dx of 1. Now we have y. Now this is a differential function provided x is not equal to minus 5. Since it's the output, so it cannot be negative. So as x represents outputs, so x greater than or equal to 0. Therefore, y equal to 3x into x plus 7 by x plus 5 plus 4 is a differentiable function. Is a differentiable function. Now we differentiate this dx of 1. Now 3 is a constant, we keep it outside. Now it is a u v rule. So u dx of v, so this one x plus 5 whole square, x plus 5 into 1 minus x plus into 1 plus x plus 7 by x plus 5 into 1. And dx of 4 is 0. So this is what we have got. 3 outside u dx of v plus v into dx of u. Now, if we simplify this one, what we get? It is 3 outside x into minus 2 by x plus 5 whole square plus x plus 7 by x plus 5. On further simplification, 3 into x square plus 10x plus 25 plus 10 divided by x plus 5 whole square. 3 into x plus 5 whole square plus 10 divided by x plus 5 whole square. This gives us 3 into 1 plus 10 by x plus 5 whole square. So as x increases, x plus 5 whole square increases. So 10 by x plus 5 whole square decreases. Therefore, dx of y decreases. marginal cost falls as output increases. X greater than ln 1 plus x for all x belongs to. First of all, we define fx equals to x minus ln x square plus 1 for all x. Now this is a combination of, you can see here is a difference of a linear function and a logarithmic function. So fx must be differentiable. Fx is a differentiable function. So f dash x equals to 1 minus 2x by x square plus 1. This one simplification we get x square minus 2x plus 1 by x square plus 1. This gives us x minus 1 whole square by x square plus 1. Now, f dash x greater than 0. Now, you can understand here that when x is 1, then it will be equal to 0. But if I eliminate that part, then it is greater than 0. Here, f dash x is equal to 0 when x is equal to 1. We find after this f double dash x. What we get? It is x square plus 1 whole square 2 into x square plus 1 minus 4x square equal to 2 into x square minus 1 by x square plus 1 whole square. This is f double dash x. Now this can be further simplified as 2 into x plus 1 into x minus 1 divided by x square plus 1 whole square. We take a number line minus 1 plus 1. We observe here that this is always greater than 0, only this part. So here on the right hand side, it is plus power or sign changes, power or sign changes. So from this, we understand that f double dash x changes its sign on two sides of x equals to 1. Hence, fx is strictly monotonic, increasing at every x not equal to 1. And x equal to 1 was what? X equal to 1 is a point of inflection. Why? Because it changes sign on two sides of x equal to 1. Hence, what we say that fx is strictly strictly monotonic increasing at every x except 1. And 1 is what? 1 is a point of inflection. So separately we can check for 1 also. So here f double dash is sign on two sides of this. You write it down and then you see fx is strictly monotonic increasing at every x and x equal to 1 is the point of inflection. Is the point of inflection. We observe 1 equal to ln e greater than ln 2 equal to ln 1 square plus 1. So at 1, what we observe, 1 is greater than ln 1 square plus 1. At 1, 1 is greater than ln 1 plus square plus 1. So according to our proof, what we need to prove x is greater than this one. First thing, at 1, we are sure that that equation holds true. The inequality holds true. This shows that the inequality which we are going to prove holds true. So here what we can say that 1 greater than this one. So x greater than ln x square plus 1 holds true for x equal to 1. Now the rest part, that is, we have to show for the other values it is true. How? See, as f dash x greater than 0, so fx is strictly increasing increasing. Now fx is continuous. Fx is continuous at x equal to 0. Therefore, fx is strictly increasing for all x belongs to 0, comma infinity minus set counting 1. And then we can write fx greater than f of 0 for all x belongs to r plus minus 1. And this says x minus ln x square plus 1 greater than 0. And this says x greater than ln x square plus 1. Now we consider this one as statement 1 and this one statement 2. On combining 1 and 2, we get x greater than ln x square plus 1 for x greater than 0. So that is the proof. It is given x greater than 0. First part. Show that x greater than ln x square plus 1. Now here, for this type of cases, what we do, we consider a function first that let fx equals to x minus ln x square plus 1. Now, this is a polynomial function of degree 1, that is linear function. This is a logarithmic function. difference, it should be differential function. So we can write it down. Fx is the differential linear function and a logarithmic function So it is a differentiable function. So it is a differentiable function. Now on differentiating what we get, f dash x equal to 1 minus 2x by x square plus 1. Which on simplification we get x square minus 2x plus 1 by x square plus 1. X minus 1 whole square by x square plus 1. Now, for all x belongs to 0, 1, f dash x is greater than 0. So fx is strictly increasing. Fx is strictly increasing function. Fx is continuous at x equal to 1. F is continuous at x equal to 1. So fx is strictly increasing for all x belongs to 0, 1. Now, belongs to 1 to infinity, f dash x greater than 0. Therefore, fx is strictly increasing in this interval also. So combining the last two discussion, that is f dash x is greater than 0 here, strictly increasing for this interval at 1 is continuous, so function is strictly increasing in this interval. And if we combine this whole thing, we can say that therefore fx is strictly increasing for all x belongs to 0, infinity. Now what we have to show? We have to show that this is greater than this one. Further, we need the help of 0 also. Because if I can show f is greater than f of 0, then we are done. Now for that, this function has to be continuous at x equal to 0. For this, function has to be continuous at x equal to 0. Up to this, we have shown that for any number, if we take greater than 0, and if we follow the concept of strictly increasing function, what we can see that when x2 greater than x1, fx2 will be greater than fx1. Now here the starting number, if I can make it 0, and f of 0 is 0 if I can show, then I can show that fx is greater than 0 for all x belongs to this one, this interval. So for that, I have to show the function is continuous at x equal to 0. So for that, we write fx is continuous. Fx is continuous at x equal to 0. Therefore, fx is strictly increasing for all x belongs to 0, infinity. This implies f of x greater than f of 0. This implies x minus ln 1 plus x square greater than 0. And this implies x greater than ln 1 plus x. That is what I need to do. log 1 plus x greater than 0. Now we consider here that let fx equals to x minus ln 1 plus x, as fx is the difference of a linear function and logarithmic function. So fx is a differentiable function. So we differentiate this and we get 1 minus 1 by 1 plus x. So x by x plus 1 greater than 0 for all x greater than 0. So fx is strictly increasing. Fx is strictly increasing for all x belongs to 0, comma infinity. Now fx is continuous at x equal to 0, because f of 0 will get 0. Here limiting value at x equal to 0, that will be also 0. So what we say that fx is strictly increasing for all x belongs to closed 0, open infinity, and therefore f of x greater than f of 0, which is 0, and this implies x minus ln 1 plus x greater than 0, and this implies x greater than ln 1 plus x when x greater than 0. What we have to show? X greater than sin x when x greater than 0. Now we consider here the graph of both the functions. Y or 0, y prime, x prime. We take the graph of sin x. And here we take the graph of y equal to x. Y equal to sin x. Okay. Now here we say after x equals to 1, fx is becoming 1. At x equals to 1, x is becoming y equal to x. This line is having the output as 1. And sin x returns the value 1 at pi by 2, which is the maximum value for sin x. And after that, y equal to x line is strictly above this y equal to sin x. So the thing is that if we can show that x is greater than sin x for x belongs to 0 to pi by 2, then automatically after that it will be greater than 1. So we'll try to focus over the interval x from 0 to pi by 2. Right now we observe at x equals to 1, y equal to x equal to some gx. So g of 1 equal to 1 and hx equal to sin x. H of pi by 2 equal to 1, which is the maximum value for hx, which is max value for hx. Now, when x greater than pi by 2 or greater than equal to pi by 2, x greater than sin x, as x greater than 1 and sin x less than equal to 1 for all x belongs to R. So we'll focus over 0 to pi by 2 only for single increasing part. So we consider x belongs to 0 to pi by 2 and we consider a function fx equal to x minus sin x. Now here gx and hx, that is actually here fx equal to x minus sin x means gx minus hx. Here gx is a linear polynomial function, and hx is a x is a sine function. Both are differentiable function. Both are differentiable function. Fx equals to gx minus hx is differentiable. Therefore, we find f dash x is 1 minus cos x greater than 0 for all x belongs to 0, pi by 2. Therefore, fx is strictly increasing. Fx is strictly increasing for all x belongs to 0, pi by 2. Now, fx is continuous at x equals to 0. Therefore, fx is strictly increasing for all x belongs to 0, pi by 2. Now, why it is continuous? Because we can check f of 0 equal to limit x to 0, f of x. So, it's strictly increasing for 0 to infinity. And this implies f of x greater than f of 0, which is 0. What is f of x? X minus sin x greater than 0. And this gives x greater than sin x, which is the point.